Hello students, in today's class we will study about colligative properties and determination of molar mass. And the contents of this lecture are as per the syllabus of class 12 chemistry, and this is further rationalized by NCERT for the year 2023-24. All the points discussed in this session are very interesting and important. Please note down these points as the same will help you in your examinations. Colligative properties and determination of molar mass. We have studied earlier that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. Hence, colligative properties are the properties which depend on the number of solute particles, irrespective of their nature, relative to the total number of particles present in the solution. The properties of solutions which are connected with the decrease of vapor pressure are: first one, relative lowering of vapor pressure of solvent. Second one is depression of freezing point of solvent. And the third one is elevation of boiling point of solvent. And the fourth one is osmotic pressure of the solution. The word colligative is taken from the Latin word co means together, ligare means to bind. Relative lowering of vapor pressure. The vapor pressure of a solvent in the solution is less than that of pure solvent. That is, according to Raoult's law, the lowering of vapor pressure depends only on the concentration of solute particles and it is independent of their identity. So, this statement can be written as P1 is equal to X1 P1 naught. Let it be equation 22. In this equation, P1 is the vapor pressure of the solution of the solvent in the solution, X1 is the molar fraction, and P1 naught is the vapor pressure of pure solvent. Now, if you want to calculate delta P1, that is the relative reduction in vapor pressure or the change in the vapor pressure, and it is given by delta P1 is equal to P1 naught minus P1. That is equal to, we can write P1 naught minus P1 naught X1. This we are putting the value of P1 from equation 22. So therefore delta P1 equals P1 naught minus P1, that is P1 naught minus P1 naught X1. So it can be further simplified into delta P1 is equal to P1 naught, taking P1 naught common, into 1 minus X1. Let it be equation 23. We also know that the total molar fraction is 1, that is X2 plus X1 is equal to 1. So the equation 23 becomes delta P1 is equal to X2 P1. Let it be equation 24. In a solution containing several non-volatile solutes, the lowering of vapor pressure depends on the sum of mole fraction of different solutes. Now again consider the equation delta P1 is equal to P1 naught minus P1. In this equation, divide both left hand side and right hand side by P1. We get delta P1 by P1 naught is equal to P1 naught minus P1 by P1 naught. So from this equation, but from equation 24, delta P1 by P1 is x2. So delta P1 by P1 naught is equal to P1 naught minus P1 divided by P1, but delta P1 by P1 naught is x2. So you please write it as x2. Let it be equation 25. The left hand side of the equation 25 is called relative lowering of vapor pressure, and it is equal to the mole fraction of the solute. That is delta P1 by P1 naught is equal to x2. Hence x2 is the mole fraction. I will read this sentence once again. The left hand side of equation 25 is called relative lowering of vapor pressure, and it is equal to the mole fraction of the solute. Now put x2 is equal to N2 by N1 plus N2. That is, we are writing the mole fraction in terms of number of moles. So equation 25 becomes P1 naught minus P1 divided by P1 naught is equal to N2 by N1 plus N2. That is, we have put the value of N2. So let it be equation 26. In equation 26, N1 and N2 are the number of moles of solvent and solute respectively. So N1 is the number of moles of solvent and N2 is the number of moles of solute. For dilute solution, N2 is far less than N1, or N1 is far greater than N2. Hence, we can neglect the value of N2 in the cases of dilute solutions. Hence, equation 26 becomes P1 naught minus P1 divided by P1 naught equals N2 by N1 in the case of dilute solutions. So let it be equation 27. We can also write equation 27 in terms of mass and molar mass. We know that the number of moles N2 is given by W2 by N2 and N1 is W1 by M1. Putting these values, we get the equation 28. That is P1 naught minus P1 divided by P1 naught is equal to W2 by M2. That is M2, and N1 is W1 by M1, and M1 goes to the numerator by rearranging. Here W1 and W2 are masses and capital M1 and capital M2 are molar mass of the solvent and solute respectively. Elevation of boiling point. The vapor pressure of a liquid increases with increase of temperature, and it boils at a temperature at which its vapor pressure is equal to the atmospheric pressure. So as we increase the temperature, the vapor pressure also increases. For example, water boils at 373.15 Kelvin because at this temperature the vapor pressure of water is 1.013 bar, that is 1 atmosphere. Further, the vapor pressure of the solvent decreases in the presence of non-volatile solute. Please see the figure shown on the screen above. This figure shows the vapor pressure of the pure solvent, which is shown in the red line, and the solution, that is a blackish line, is for solution. So these are the vapor pressure versus temperature. Temperature is plotted on the x-axis and vapor pressure on the y-axis. The boiling point of solution is always higher than that of the boiling point of the pure solvent in which solution is prepared. Please see here, for solution the boiling point is Tb, and whereas for the solvent it is Tb naught. So Tb is always greater than Tb naught, and the difference of these two is given by delta Tb. Similar to the lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than nature. So the the elevation of boiling point also depends on the number of solute. For example, a solution of 1 mole of sucrose in 1000 grams of water boils at 373.52 at 1 atmospheric pressure. Now we will do some mathematical calculation to determine the elevation of boiling point. Let Tb naught be the boiling point of pure solvent and Tb be the boiling point of the solution, as shown in the figure on the right hand side. The increase in boiling point from Tb naught to Tb, it can be written as delta Tb equals Tb minus Tb naught, and this is delta Tb is known as elevation of boiling point. It has been experimentally shown that the dilute solution, for the case of dilute solutions, the elevation of boiling point at delta Tb is directly proportional to the molar concentration of the solute in the solution. So we can write delta Tb is proportional to small m, where m is the molar concentration. So equation 29 can be written as delta Tb is equal to Kb into m, where K subscript b is the constant of proportionality. Let it be equation 30. So Kb is called the boiling point elevation constant, or molar elevation constant, or ebullioscopic constant, the constant of proportionality. The unit of Kb is Kelvin kg per mole. If W2 grams of solute of molar mass M2 is dissolved in W1 grams of solvent, then the molality m small m of the solution is given by the expression m is equal to W2 by M2 divided by W1 into 1000. Here the value of W1 is taken as 1 kg. So that can be rearranged as 1000 W2 divided by M2, capital M2 into W1. Here capital M2 is the molar mass of the solute. Now recalling the equation 30, we can write delta Tb as delta Tb is equal to Kb Kb as it is into m. The value of m is substituted from equation 31. That is m, small m is equal to Kb into 1000 into W2 divided by m2 into W1. Let it be equation 32. So from equation 32, if we know the values of all other terms like delta Tb, Kb, W2 and W1, we can calculate the molar mass M2 of the solute. And this is given by M subscript 2 is equal to Kb into 1000 into W2 divided by delta Tb into W1. Let it be equation 33. Thus, in order to determine M2, molar mass of the solute, known mass of solute is in a known mass of solvent is taken and delta Tb is determined experimentally for a known solvent whose Kb value is to be calculated or whose value of Kb is known. Example number 6. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 grams when added to 39 grams of benzene whose molar mass is 78 grams per mole. The vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? So please read the question once again and note down all the given parameters. Let us solve it. So the vapor pressure of pure benzene, that is P1 naught, is given as 0.850 bar. The vapor pressure of the solution of benzene in solution is given as 845 bar, and molar mass of benzene is given as M1 is equal to 78 grams per mole. Weight of the solid non-volatile solute is W2 is equal to 0.5 grams, and the weight of the solution is given as 39 grams. Now we have to calculate the molar mass M2 of the substance using formula P1 naught minus P1 divided by P1 naught equals W2 into M1 divided by M2 into W1. Please substitute the values of the given parameters in this equation and calculate. The result is we will get the value as M2 is equal to 170 grams per mole. Next question. 18 grams of glucose, that is C6H12O6, is dissolved in 1 kg of water in a saucepan. At what temperature will the water boil at 1.013 bar? Kb for water may be taken as 0.52 Kelvin kg per mole. Please read the question once again and note down the values. Moles of glucose is equal to 18 gram divided by 180 grams per mole. This you have to calculate from the formula. So therefore, moles of glucose will be 0.1 mole. So number of kilograms of solvent is equal to 1 kg because it is given that it is dissolved in 1 kg of water. So therefore, the molality of glucose solution is 0.1 mol per kg. For water, the change in boiling point is delta Tb is equal to Kb into small m. So Kb is given as 0.52 Kelvin kg per mole into small m is 0.1 mole per kg, that is equal to 0.052 Kelvin. Since water boils at 373.15 Kelvin at 1.013 bar pressure, therefore the boiling point of solution will be 373.15 plus 0.052 Kelvin, that is equal to 373.202 Kelvin. Next example. The boiling point of benzene is 353.23 Kelvin. When 1.8 grams of non-volatile solute is dissolved in 90 grams of benzene, the boiling point is raised to 354.11 Kelvin. Calculate the molar mass of solute. Kb for benzene is 2.53 Kelvin kg per mole. Please read the question once again and we will go ahead with the solution. The boiling point elevation is given by 354.11 minus 353.23, that is equal to 0.88 Kelvin. Substituting the value of delta Tb in the equation, M2 is equal to Kb into 1000 into W2 divided by delta Tb into W1. So we get Kb is 0. Kb is given as 2.53 Kelvin kg per mole, 2.53 into 1000 into 1.8 grams, that is the weight of the solute, divided by 0.88 Kelvin into 90 grams. So the weight of solution is 90 grams. So we get the value as 58 grams per mole. The lowering of vapor pressure of a solution causes the lowering of freezing point as compared to that of pure solvent. Please see the figure shown on the figure wherein a plot of temperature versus vapor pressure is shown. Temperature is plotted on x-axis and vapor pressure on the y-axis. Here, the lowering of vapor pressure has caused the lowering of freezing point. See, for example, the red line or the orange line is for liquid solvent and dark line is for solution. When the pressure is lowered, the freezing point of liquid solvent has fallen. So this decrease in freezing point, noted as delta Tf equals Tf naught minus Tf, is called depression in freezing point. Let Tf naught be the freezing point of pure solvent and Tf be the freezing point when non-volatile solute is dissolved in it. See here, the original freezing point was Tf naught of the pure liquid solvent, and after it is it is dissolved in a solution, the freezing point has fallen to Tf. Similar to the elevation of boiling point which we discussed in the previous slide, the depression of freezing point delta Tf for dilute solution, that is ideal solution, is directly proportional to the molality small m of the solution. Therefore, delta Tf is proportional to m, and eliminating and substituting with the constant of proportionality, we get delta Tf is equal to Kf into m. Let it be equation 34. Here, the proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or molar depression constant or psychroscopic constant. The unit of Kf is Kelvin kg per mole. Values of Kf for small common salts are listed in the table given in the next slide. If W2 grams of solute having molar mass M2 present in W1 grams of solvent produces the depression in freezing point of the solvent, then molality of the solute is given by the equation M is equal to W2 by M2 divided by W1 divided by 1000. That is 1000 W2 divided by M2 into W1. Let it be equation 31. Substituting the value of molality small m in equation 34 given in the previous slide, we get delta Tf is equal to Kf into W2 by M2 divided by W1 into 1000. Therefore, simplifying, we get Kf into W2 into 1000 divided by W1 into M2. Let it be equation 35. So, we can find M2 from equation 35 by rearranging it as M2 is equal to Kf into W2 into 1000 divided by W1 into delta Tf. Let it be equation 36. Thus, for determining the molar mass M2 of the solute, we should know the quantities W1, W2, delta Tf along with the molar freezing point depression constant Kf. The values of Kf and Kb, which depend on the nature of solvent, can be ascertained from the following relations. So Kf is equal to R into M1 into Tf square divided by 1000 into delta fusion into H. Let it be equation 37. Kb is equal to R into M1 into T square B divided by 1000 into delta vapor into H. Here symbols R and M1 stand for gas constant and molar mass of the solvent respectively, and Tf and Tb denote the freezing and boiling point of pure solvent respectively in Kelvin. Further, delta fusion H and delta vapor H represent the enthalpies of fusion and vaporization of solvent respectively. So the table shown on the screen depicts the boiling point per Kelvin and the constant Kb, the values of Kb and the values of Kf. It also shows the depression in the boiling point and freezing point. So for water, boiling point is 373.15 and the value of constant Kb is 0.52 Kelvin per Kelvin kg per mole. That is, Kb is in Kelvin kg per mole. So freezing point of water is 273 Kelvin. So the value of Kf is 1.86. Similarly, for all other solvents like ethanol, cyclohexane, benzene, chloroform, carbon tetrachloride, carbon disulfide, diethyl ether, acetic acid are shown. Please note down the molar boiling point elevation and freezing point depression constant for some solvents from this table. What examples? Example number 9. 45 grams of ethylene glycol, that is C2H6O2, is mixed with 600 grams of water. Calculate A, the freezing point depression, and B, the freezing point of the solution. Answer. Depression in freezing point is related to molality. So therefore molality equals moles of ethylene glycol divided by mass of water in kilogram. First we have to calculate the moles of ethylene glycol. That is given by moles of ethylene glycol is equal to the weight of ethylene, mass of ethylene glycol, that is 45 grams, divided by the molar mass. Molar mass of ethylene glycol is 62 grams per mole. That is equal to, simplifying, we get 0.73. This 62 grams per mole is calculated as it is. The formula, the empirical formula is C2H6O2. That is equal to 12 into 2 plus 6 into 1 plus 2 into 16. That's equal to 62 grams per mole. Therefore, mass of water in kg is 600 grams per 1000 kg. That is equal to 0.6 kg. Hence, molality of ethylene glycol is 0.73 divided by 0.6 kg. That is equal to 1.2 moles per kg. The freezing point depression is given by the formula delta Tf is equal to Kf into m, where delta Tf is the freezing point depression and Kf is the constant and m is the molality. Therefore, delta Tf is from the table 1.86 K Kelvin kg per mole from the table given in the previous slide into 1.2. That is molality. Small m is 1.2. So we get the value of delta Tf as 2.2 Kelvin. Therefore, freezing point of aqueous solution is equal to 273.15 Kelvin minus 2.2 Kelvin. That is equal to 270.95 Kelvin. Next question. 1 gram of non-electrolyte solution dissolved in 50 gram of benzene lowers the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kg per mole. Find the molar mass of the solute. Substituting the values in the formula, M2 is equal to Kf into W2 into 1000 divided by W1 into delta Tf. Here M2 is the molar mass, Kf is the freezing point depression constant, W2 is the mass of the electrolyte, W1 is the mass of the solute into delta TF of the solution. W1 is the mass of the solution. Therefore, it is 5.12 Kelvin kg per mole into 1000 grams per kg divided by 0.4 into 50 grams. Simplifying, we get the answer as 256 grams per mole. Thus, molar mass of solute is 256 grams per mole. Osmosis and osmotic pressure. Osmosis is the movement of water across a semi-permeable membrane from an area of low solute concentration to an area of high solute concentration. First, let us understand by the term semi-permeable membrane. Semi-permeable membranes. These membranes can be of animal or vegetable origin, and these occur naturally, such as pig's bladder or fragment, or can be of synthetic, such as cellophane. These membranes appear to be continuous sheets of films, yet they contain a network of submicroscopic holes or pores. So, small solvent molecules like water can pass through these holes, but passage of bigger molecules like solute is hindered. First of all, let us assume that only solvent molecules can pass through these semi-permeable membranes. If this membrane is placed between a solvent and the solution, the solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of solvent is called osmosis. The flow will continue till equilibrium is attained. The flow of solvent from its side to solution side across a semi-permeable membrane can be stopped if extra pressure is applied on the solution. The pressure that stops the flow of solvent is called osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. The important point to be kept in mind is that the solvent molecules always flow from lower concentration to the higher concentration. Osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis. In the figure, the solution and solvent are contained in the container separated by a semi-permeable membrane SPM. An excess pressure pi must be applied to a solution to prevent osmosis, that is, to stop the passage of solvent molecules through a semi-permeable membrane into the solution. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to molarity, represented by the symbol capital C, of the solution at a given temperature T. Hence, we can write the equation as osmotic pressure pi is equal to capital C into capital R into capital T. Here, pi is the osmotic pressure and R is the gas constant, which can be further written as pi is equal to N2 by V into R into T. Here C is equal to N2 by V, where N2 is the moles of solute and V is the volume. If W2 grams of solute of molar mass M2 is present in the solution, then N2 equals W2 by M2. As we know, it is the mass divided by molar mass. That is, the number of molecules will be equal to mass divided by the molar mass. And we can write equation 40 as pi into V cross multiplying equals W2 into RT divided by M2, or M2 equals W2 RT divided by pi into V. Let it be equation 42. Now we will further describe the isotonic, hypotonic and hypertonic solutions. Before that, measurement of osmotic pressure provides another method of determining molar masses. This method is widely used to determine molar masses of the proteins, polymers and other macromolecules. The osmotic pressure method has the advantage over the other methods as pressure measurement is around the room temperature and molarity of the solution is used instead of molality. As compared to other colligative properties, its magnitude is large even for a dilute solution. The technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules as they are generally not stable at higher temperatures and polymers have poor solubility. Isotonic, hypotonic and hypertonic solution. Two solutions having the same osmotic pressure at a given temperature are called isotonic solutions. So, solutions having the same osmotic pressure at a given temperature are called isotonic solution. If one solution is of lower osmotic pressure, it is called hypotonic with respect to the more concentrated solution. The more concentrated solution is said to be hypertonic with respect to dilute solutions. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. Please see the figure which depicts the reverse osmosis which occurs when a pressure larger than the osmotic pressure is applied to the solution. Here on the right hand side, the piston applies a pressure larger or greater than the osmotic pressure. That is, now the pure solvent flows out of solution through the semi-permeable membrane. So when we put salt water here, pure water comes out of the semi-permeable membrane. This phenomena is called the reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater. When a pressure more than the osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable support. The cellulose acetate is permeable to water but impermeable to the impurities. That means it does not allow the impurities or ions present in seawater to flow through the semi-permeable membrane. These days, many countries use desalination plants to meet their potable water requirements. We'll answer some selected multiple choice questions. Question number 1. The relative lowering in vapor pressure is proportional to the ratio of the number of. So, four options are given. Please read these following four options given on the screen yourself. Four options. So, now we have to analyze by applying the formula P1 naught minus P1 divided by P1 naught is equal to N2 divided by N1 plus N2, where P1 naught is the vapor pressure of pure solvent, P1 is the vapor pressure of the solution, N2 is the number of moles of solution 2, N1 is the number of moles of solution 1. So, we know from this formula it is the ratio of number of molecules to the total number of molecules. So, total number of molecules is N1 plus N2. N2 divided by N1 plus N2. So, option C is the correct answer. Next question. Vapor pressure of a pure liquid X is 2 atmospheres at 300 Kelvin. This is lowered to 1 atmosphere on dissolving 1 gram of Y in 20 grams of liquid X. If molar mass of X is 200, what is the molar mass of Y? Please note down all the given parameters and work out. You are given four options. You have to select the correct answer. The four options are 20, 50, 100 and 200. The molar mass. So let us analyze. So apply the formula P1 naught minus P1 divided by P1 naught is equal to W2 into M1 divided by M2 into W1. Substituting P1 naught is 2, P1 is 1 and P1 naught is 2. That is equal to weight of Y is given as 1 gram and molar mass of Y we have to calculate into molar mass of X is 200 and weight of X is 20 grams. This is given. So substituting all these values and calculating My is equal to 20 and this is given as option A. Next question. A solution containing 12.5 grams of non-electrolytic substance in 185 grams of water shows boiling point elevation of 0.8 K. Calculate the molar mass of the substance. And it is given that boiling point elevation constant is Kb equals 0.52 Kelvin kg per mole. Four options are given which appear on the screen. A is 53.06 grams per mole. Option B is 25.3 grams per mole. Option C is 16.08 grams per mole. Option D is 43.92 grams per mole. So you have to make some calculation as shown on the screen in the insert box. Apply the formula M2 is equal to Kb into 1000 into W2 divided by delta Tb into W1. So that substituting Kb is equal to 0.52 given and W2 is 12.5 grams and 1000. If we want to convert it into kg, we have to multiply by 10 to the power of minus 3. So this 1000 and the multiplication factor of Wt get cancelled, and at the new denominator we have delta Tb is given as 0.8 into 0.185. So 185 grams is 0.185 kg. So substituting these values, we get 43.92 grams per mole, and this is given as option D. Please mark it. Next question. Sprinkling of salt helps in clearing the snow-covered roads in hills. The phenomenon involved in this process is, you please, four options are given. Identify the correct answer. Option A, lowering of vapor pressure of snow. Option B, depression in freezing point of snow. Option C, increasing the freezing point of snow. And option D is melting of ice due to increase in temperature by putting salt. So the analysis part is, when salt is spread over snow, the snow starts melting from the surface because of depression in freezing point and helps in clearing the roads. So the correct option is option D. There is depression in freezing point of snow. Next question. Osmotic pressure of a solution can be increased by, four options are given. Increasing the volume. Option B, increasing the number of solute molecules. Option C, decreasing the temperature. Option D, removing the semi-permeable membrane. So we have to apply the formula. Osmotic pressure pi is equal to N divided by V into R into T, where pi is the osmotic pressure, N is the number of molecules, V is the volume, R is the gas constant, and T is the temperature. Therefore, using this formula, pi is proportional to N. So we can increase the osmotic pressure by increasing the number of solute molecules. That is, option B is the correct answer. Next question is, a 5% solution of cane sugar molecular weight is equal to 342 is isotonic with 1% solution of substance X. The molecular weight of X is four options are given. You please read it and analyze the problem question. So we know that isotonic solutions are those solutions having the same osmotic pressure at a given temperature. So applying, being isotonic, the molar concentration of cane sugar should be equal to molar concentration of the substance X. Therefore, 5 by 342 into 1000 divided by 100 equals 1 by x into 1000 divided by 100. Therefore, x is 342 by 5. That is cross multiply. Take x to the numerator and cross multiply. We get answer as 68.4, which is given as option B. Please mark it. Next question. A solution containing 10.2 grams of grams of glycerin per liter is isotonic with a 2% solution of glucose. What is the molecular mass of glycerin? Four options are given. A 91.8 grams, option B 1198 grams, option C 83.9 grams, option D 890.3 grams. So let us do some calculation. Osmotic pressure of glycerin should be equal to osmotic pressure of glucose because this is both are isotonic solutions. Therefore, N1 by V1 into RT should be equal to N2 by V2 into RT, where N, R, N, V, R are usual notations. Substituting as shown on the screen, that is N1 is equal to 10.2 divided by M, M2 into 1 over 1 equals 2 over 180 into 1000 divided by 100. That M is equal to 91.8. So density of water is 1 grams per centimeter cube. Therefore, 91.8 is the answer given as option A. Please mark option A. Please mark it. Which of the following statement is correct? A saturated solution will remain saturated at all temperatures. Option B. A plant cell swells when placed in hypertonic solutions. Option C. The depression in freezing point is directly proportional to the molality of the solution. Option D is lowering in vapor pressure is a colligative property. So we have to remember and mark option C as the correct answer. With we come to the end of the part of colligative properties of solutions. Next lecture we will take up abnormal molar masses. Till then, goodbye.